Hello everyone, I am Aditya and this is my MSc Computer Science project, Crawling and Search Engine System with semantic search, BM25 ranking, web crawling and hybrid retrieval. The objective of this project is to design and implement a miniature search engine from scratch. Instead of relying on existing search engines, the system performs every major task independently. It begins by crawling websites, extracts useful information from web pages, stores that information in the database, builds an inverted index for efficient retrieval, generates semantic embeddings for understanding meaning, and finally retrieves and ranks documents using a combination of traditional information retrieval techniques and semantic search. This project demonstrates the complete workflow of modern search engine, starting from discovering web pages and ending with presenting highly relevant search result. Before discussing the implementation, let's first understand the problem. The World Wide Web contains an enormous amount of information distributed across millions of web pages. Users expect search engines to retrieve the most relevant pages within milliseconds. Building such a system involves several independent components. First, we need a crawler that can automatically discover pages. Second, the crawler must extract useful information from each page. Third, the extracted content must be indexed efficiently. Fourth, the search engine must understand both keywords and the semantic meaning of user queries. Finally, all retrieved documents must be ranked according to their relevance. This dissertation focuses on implementing each of these components as a complete end-to-end search engine pipeline. The overall architecture of the project consists of 5 major modules. The first module is the web crawler. The crawler discovers new pages by following hyperlinks while respecting robot.txt policies and crawl depth limitations. The second module is content extraction module. This module extracts useful information such as page title, meta description, visible text content and outgoing links. The third module is the indexing engine. Here is the extracted data is tokenized, cleaned and converted into an inverted index for efficient keyword retrieval. At the same time, dense semantic embeddings are generated and stored inside PostgreSQL using pgvector extension. The fourth module is the search engine itself. When a user submits a query, the system performs both BM25 keyword retrieval and semantic similarity search. Finally, the hybrid ranking module combines both scores and returns the most relevant documents through the fast API backend. Now let's see how the crawler is implemented. Now I will explain the crawler implementation. The crawler begins with one or more seed URLs provided by the user. Instead of using recursion, the crawler uses an iterative priority queue implemented with Python's heap queue model. Every nearly discovered URL is assigned a priority score. This score is calculated using 3 factors. The first factor is crawl depth. Pages closer to the seed URL receives higher priority because they are generally more important. The second factor is URL importance. Pages containing keywords such as docs, tutorial, about, or help receive additional priority. The third factor penalizes low value pages such as login, sign up, admin, checkout, cart pages as they contain less important content. The crawler always removes the highest priority URLs from the priority queue first. Before downloading a page, a crawler checks the website's robot.txt file to ensure that crawling is permitted. If a sitemap is available, the crawler automatically discovers URL from the sitemap to improve coverage. Let me show you it by practical. I will run my crawler.py. You can see I have given a seed URL for Python, official Python website, website. Yeah. Let's see how it crawls. As I said, it firstly checks for the sitemap. If no sitemap is found, then it fallbacks to the seed URL and discovers new internal links. As you can see, it is discovering new and new links. And if I have crawled the web page earlier and the content of that web page is not changed, then you can see I have logged information like, is this a new page? No, false. Then it will not crawl that again or store its information again. It will skip that page and look for another pages that will either it should be new or it should have a changed content. For tracking that, I every time I check the hash content of a page which is crawled earlier. If the content of that web page is changed, then only the crawling on that web page will happen. As you can see, it is discovering more and more URLs. At this time, it has already discovered 34 links and visited them. The crawler also performs URL normalization to eliminate duplicate URLs created due to trailing slashes, fragments, or relative paths. Only internal links belonging to the same domain are followed. Non-HTML resources such as PDF files or images are ignored totally. Once the page is successfully downloaded, Beautiful Soup parses the HTML document. The system extracts the title, meta description, visible paragraph text, and all outgoing hyperlinks. Finally, this structured information is followed to indexing module for storage. The extracted information is stored inside PostgreSQL. The pages table stores complete information about every crawled document, including the URL, title, description, content hash, HTTP status code, crawl depth, crawl timestamp, embedding vector, and additional metadata. The terms table. Let me show you the terms table schema. Yeah. It stores every unique key token present across the collection. Let me show postings. The postings table forms the inverted index by connecting each term with pages in which it appears, along with its frequency. Let's see links table. The links table stores the hyperlink graph by recording relationships between source pages and destination pages. This database schema enables efficient retrieval while also supporting incremental crawling and future reindexing. After the content is stored, the indexing process begins. Let me show you the indexing. Yeah. The text is first processed during pre-processing. All text is converted into lowercase, punctuation is removed, stop words are filtered, and meaningful tokens are extracted. The title receives a higher weight than the body because title usually describes the document more accurately. Similarly, the metadata description is also assigned additional weight. The resulting tokens are inserted into the terms table if they do not already exist. For every occurrence of the term inside a document, the corresponding frequency is stored inside the postings table. This creates an inverted index, allowing the search engine to directly locate documents containing specific terms without scanning the entire database. At the same time, every document is converted into a semantic embedding using a sentence transformer model. These three 8 4-dimensional vectors uh, are stored using PostgreSQL's PG vector extension. This allows efficient nearest neighbor similarity search during semantic retrieval. Okay, let's see the search engine front end, how it looks, and give some queries to it, and discuss how searching works. When the user searches for a query, like this, you can see the query first undergoes pre-processing similar to document pre-processing. The system then performs two retrieval operations simultaneously. The first retrieval method is BM25. BM25 is a traditional probabilistic ranking algorithm that evaluates keyword relevance based on a term frequency. Inverse document frequency, and document length normalization. The second retrieval method is semantic search. The user is converted into a dense embedding vector using same sentence transformer model. This query vector is compared with document vectors stored inside PostgreSQL using cosine similarity. Documents with similar meanings receive higher semantic scores even if they do not contain identical keywords. Finally, hybrid ranking combines both scoring using a weighted formula. You are seeing the hybrid ranking here. It is the combination of both lexical searching and semantic search in combination. Hybrid score equals alpha multiplied by the BM25 score plus beta multiplied by semantic similarity score. This approach combines the precision of keyword matching with the flexibility of semantic understanding. The highest ranked documents are returned to the front end through fast API as JSON responses and displayed to the user. I will show you now all the three searching methods I have mentioned earlier. Suppose I search for Python DSA. You can see here in the URL. Then you can see these types of web pages are ranked, like they are semantically very close to the query I have given here, Python DSA. So you can see here official Python website is came. Let's change the model. Let's change it to traditional lexical searching. Now let's change the searching model from semantic. Let's see what hybrid model gives search results. See, hybrid model combines both semantically close search results, also lexical accurate search results. And finally, hybrid ranking combines both retrieval methods and produces more accurate search results than either method individually. To conclude, this dissertation demonstrates the complete implementation of hybrid search engine. This project successfully integrates ethical web crawling, content extraction, PostgreSQL based indexing, inverted indexing, semantic embeddings using sentence transformers, BM25 ranking, hybrid retrieval, and a fast API based search interface. Unlike traditionally keyword only systems, the hybrid approach combines exact keyword matching with semantic understanding, resulting in significantly improved retrieval quality. This project also provides a strong foundation for future enhancement such as multilingual search, query suggestion, distributed crawling, page rank computation, and large scale indexing. Yeah, this was all for this project. Thank you so much for watching this demonstration.